I'm throwing on my lead chassis engineer hat today because we really need to talk about your brakes. Specifically, I'm going to prove to you that your mushy, vague brake pedal on track day is highly likely a structural failure, not a hydraulic one. We're going to completely tear down the whole concept of caliper bridge flex.
Okay, here's our engineering blueprint. We'll be covering the physics of bridge flex, materials and structural geometry, monoblock versus two-piece calipers, track heat and brake fade, diagnostic garage tests, and finally, the engineer's upgrade checklist.
Let's dive right into Section 1, the physics of bridge flex. It's time to understand the clamshell effect.
To engineer a solution, we first have to really understand the forces at play here. Imagine you're heading into a heavy braking zone and you just stomp on that pedal. You are sending this massive wave of hydraulic pressure, often well over 1200 psi, straight into the caliper body. Now keep in mind, most floating calipers are essentially just C-shapes. The bridge is that top section connecting the two halves over the rotor. When you slam 1200 psi into a C-shape, it desperately wants to bow outward. It literally bends the iron or aluminum open like a clam. So when you press the pedal, a huge chunk of your foot travel is entirely wasted just bending the caliper body open. This is what we call the dreaded clamshell effect.
And that brings us to the real underlying issue, volumetric absorption. Basically, this is the volume of brake fluid consumed purely by the physical deformation of your caliper before any actual clamping force is even developed against the rotor. You might think, oh, my pedal is soft or just need to bleed my brakes again. But in reality, your hydraulic fluid is just filling the extra empty space created by your caliper bending out of shape. Fluid displacement is entirely masking a mechanical stiffness issue.
Moving right along to Section 2, materials and structural geometry. Let's talk about engineering around this flexibility.
From an automotive engineering standpoint, dealing with those massive hydraulic clamping loads comes down almost entirely to material choice and structural geometry. Take a look at cast iron. Sure, it's heavy, but it is naturally incredibly stiff with a very low flex tendency. Aluminum, on the other hand, is great because it sheds all that unsprung mass, but man, it flexes significantly more. To counteract this, aluminum alloys fundamentally require much thicker structural sections, just to match the natural rigidity of cast iron.
So how do we actually increase stiffness without making the caliper weigh an absolute ton? We engineer the cross-section. We have to look at the second moment of area, which is really just a fancy geometric term that dictates bending stiffness. Now, engineers can definitely use thicker bridge sections, but that adds mass. Instead, we analyze how bridge extensions work. By adding lateral ribs that extend outward and downward past the mounting bolts, we push the material farther away from the neutral axis. It's a brilliant geometric trick that significantly increases the second moment of area, delivering much higher stiffness without a massive weight penalty. Let's move over to Section 3, monoblock versus two-piece calipers, the structural showdown. When we compare these two architectures, a monoblock is machined from a single, solid chunk of material. There are no bolted joints to flex, so it's universally praised for its stiffness. Two-piece calipers, however, are bolted together, and a lot of energy gets wasted trying to force those two halves apart. But here is an absolute game changer. A well-engineered two-piece caliper that uses high-grade steel bridge bolts can actually outperform a budget monoblock in pure mechanical deformation resistance. Why? Because premium steel resists shear and tension forces far better than cast aluminum, meaning those steel bolts become an incredibly efficient load-bearing pathway. We also have to contrast the stiffness benefits of the actual mounting points. Upgrading from standard axial mounts, which sit parallel to the axle, to radial caliper mounting points that point straight in toward the hub, significantly improves resistance to braking torque flex. Radial mounting handles that rotational twisting force far better, which keeps your brake pads perfectly flat against the rotor. All right, on to Section 4, track heat and brake fade. Let's look at the racing reality. Let's see what happens when we calculate these loads at racing speeds. A little flex on the street is fine, but on the track, it's devastating. When that bridge flexes, the whole caliper tilts, causing one edge of the pad to dig in much harder than the other. This uneven pad wear creates localized hot spots on your rotor, which severely accelerates brake fade. But honestly, even worse than that, it completely ruins your brake modulation. Think about it. When you're trail braking into a hairpin at 130 miles per hour, you absolutely cannot afford a flexing bridge. Modulation just becomes a complete guessing game. And here is the ultimate thermal nightmare. Track heat fundamentally changes your material properties. As we already established, aluminum flexes more than iron, but heat actually saps aluminum's rigidity exponentially faster. A caliper that feels totally rock solid in the pit lane will deflect wildly once it's soaked in 400 degrees of radiant heat. Hot calipers simply flex more than cold calipers, period.
Section 5, Diagnostic Garage Tests. Let's go find that flex. You know, you really don't need million-dollar finite element analysis software to diagnose this stuff. Just your own two eyes and a garage. Let's outline some incredibly simple diagnostic tests to identify bridge flex without any complex equipment. Number 1, the visual observation test. Have a buddy stomp the brakes while you watch the caliper bridge with a flashlight. You are looking for tiny micro movements at the seam. Number 2, the finger deflection test. Take the wheel off and press hard on the caliper arms in the direction of rotor travel. If it moves under finger pressure, it is absolutely flexing under hydraulic pressure. Number 3, the bridge bolt check. Grab your torque wrench and ensure every single bolt on a two-piece caliper is perfectly at spec. And 4, measure your pedal travel distance to the floor. If that distance is increasing over time despite having totally fresh fluid, your structure is giving up.
Finally, Section 6, the engineer's upgrade checklist. Time to fix the structure.
So the crucial takeaway here is taking decisive action to reinforce the structure, rather than just endlessly bleeding your brake fluid hoping for a stiffer pedal. Here is your definitive upgrade checklist. First, upgrade from single piston sliding calipers, which are literally the worst offenders for the clamshell effect, to a rigid fixed or monoblock caliper. Second, if you run a two-piece setup, replace the OEM hardware with high-grade steel bridge bolts to lock those hubs together tightly. Third, and this is vital for you track guys, maintain a strict schedule for checking your bolt torque. Heat cycling naturally loosens fasteners, so retorque them after every single track weekend. And finally, if possible, upgrade to radial mounting to further limit that torque deformation.
I want to leave you with this final, somewhat provocative thought to chew on before your next track day. Are you actually upgrading your brakes, your true stopping power and thermal capacity, or have you just been treating the hydraulic symptoms of a fundamentally flexing mechanical structure? Stop chasing ghosts in your brake fluid. Look at the bridge, look at your hardware, and engineer the flex out of your braking system.